That being said, I would like to invite on our next panelists. So Andrea, Pierre, and Ed, if you can join us. Just going to take a quick look at our slides here. So now we're going to be talking about optimization for data-intensive deployments. All right, so when you get a chance, good. Nice to see you both. And just need to get Pierre on here. Very good. So as with everybody else, let's just do a quick 30-second intro about who you are and how you got into the space. We can start out with you, Andrea.
Okay, fine. So hi, everyone. I'm Andrea Carboni, and I'm an AI solution engineer working on the pre-sales side for our AI portfolio. My main role is working in Europe, helping customers in creating AI solutions, helping them in providing proof of concepts, and also participating to events to promote our products, which are based on open source components.
Fantastic. Thank you very much. How about you, Ed?
Hey, so yeah, I'm Ed Shee, head of developer relations at SELDON. So I kind of got into this space, actually. My background is kind of cloud computing, DevOps, different deployment techniques. And I had a kind of personal interest for AI and machine learning, and was doing a ton of stuff online and little pet projects. I just wanted to get way more into it. And actually SELDON was like the perfect blend of the kind of Kubernetes and cloud native world, as well as meets machine learning. So it's been a really, really fun journey. And yeah, it's great to be here.
Good. Nice to have you with us. Last but not least, Pierre. Oh, sorry, you're muted, which is very respectful. But yeah, no worries. When you get a chance, let's see. It's all good. Anyway, this is just part of the charm. In the meantime, let's share some love. It's good. You never have too much love. You're good. We got lots of love flying around. Good. Oh, not yet. Or maybe I'm being blocked out by the love. Don't worry, it's okay. We'll let the love die down. Let's see. No, not yet. Maybe if you drop out and jump back in, that's totally fine. Like I said, it's the nature of doing things live. So some people pre-record things, but it takes out that little extra edge. We are talking about edge cases. That being said, folks, as usual, keep your questions coming in the chat. We want to hear your feedback. We want to know what your doubts are so that our panels can answer them better. Let's try it now, Pierre.
Sorry about this. Do you hear me? Perfect.
Yep, it's all good. Yep.
Nice. So I'm Pierre-Nicolas. I'm the co-founder and CTO at PICSELLIA. So we are a nearly 4 years old company, and we build an end-to-end MLOps platform, but dedicated to computer vision projects. So to help companies that want to put their computer vision models in production. We take them from data collection and management up to model deployment and monitoring, and all the automations that allows to connect what is coming from the real world, the production world, to the, let's say, the research lab, or like where the data scientists can work on the model. So that's where we work on with our clients.
Good. That being said, Pierre-Nicolas, what about, when considering, we're talking about building models with edge deployment in mind, what comes first? A high-performing one, think about the pipeline from the very beginning. What's that first step? I think it's overwhelming for a lot of folks that are out there. What would you recommend?
So I think that a lot of things have been said in the conclusion of the last panel, like you have to do less. And when I mean do less, I'm not saying that regarding to the pipeline, but I mean do less regarding the model training and optimization, or like research regarding model architecture. Like basically, and this is not only for edge deployments, but you're not Google, so you might not have the data scale or like the research capabilities of like those large companies. So I would suggest that you start with like some simple pipelines that would take you from the data collection from, I don't know, so everything that I will say will be regarding like image data, and usually taken from industrial use cases. For example, we have clients working in different plants that have cameras that capture some images on treadmills or on different machines. So let's say that you do have those cameras, you want to start acquiring some data, then having, let's say, a toy model that just like predicts the right labels, but not with a great accuracy. And you just want to try out the whole life cycle. So I will deploy it on one single location in one plant, see what are the results, and then wonder how you can take this data back to, for example, some new data back to verification, so manual labeling. How do you retrain the model? How do you sample the data that is coming from production? What will be the, I don't know, deployment requirement specification, for example? So we talked a lot about like the difference between edge devices and the different hardware that exists. So that's the kind of thing that you have to focus on and that you have to put into the pipeline before trying to develop a high-performing model, to me.
Okay. You, in the beginning, you mentioned the aspect of scale. So I'd like to turn it over to Ed now. As you know, the scale of data and machine learning, grows, what does that mean for ML inference?
Yeah, so this is something that actually we've spent a lot of time on at SELDON recently, particularly with the kind of the growth in the data-centric AI movement, right? Moving from as you heard just there, right, how historically everyone tried to be Google, right, and everyone wanted to build the best model architecture and gain the smallest like percentage increase in accuracy or whatever. But didn't give enough thought to the data itself. And that's now kind of gone on its head, and people are saying, how do we get better data sets and build better models? What people haven't spent enough time thinking about is what does this actually mean for inference, right? How can we provide better data at inference? Because we can't necessarily put the onus of that on the user. So, I guess sticking with the image example from PICSELLIA, like if you've got someone who, you're doing some sort of recognition on an image that's going to come in from someone's mobile device, you can't necessarily tell them to orient that device in a certain way or set the lighting up in a certain way, right? But what you can do is a whole load of like image transformations around it afterwards once you receive that image. What this means, right, as you start to do these kind of like data operations before you even run a prediction against your model, is that you now no longer have just a single endpoint that's been deployed, and you're deploying these kind of complex machine learning systems. And that's something, I guess, at SELDON we've spent a lot of time doing over the last couple of years, partly driven by the use cases from our customers. But how can we build these kind of inference systems really, rather than just endpoints, and then monitor the data as it flows through those? Because it becomes really important to be able to identify, again, stick with the same example, like which subsets of images are we not able to classify correctly, right? If we've got that whole pipeline of data, we can go in and look and say, oh yeah, it's because maybe our like light adjusting algorithm doesn't work super well for these types of images, or from this device, or whatever it might be. So yeah, tons of things we're thinking about in that space, but I think it's a really interesting problem.
Certainly is. And another problem or opportunity that's been talked about in the different panels has been the aspect of hardware. Andrea, what is the hardware that's necessary that's going to be used to train AI models in an efficient way, right? Because in order to keep that in mind, the aspect of efficiency, what kind of hardware is going to be necessary for that?
Yeah, that is a really good question, because we have customers which are early adopters for the AI. They start with a very low number of nodes, 2, 3, 4 nodes, and up to 100 and more nodes for advanced users. And the clusters we have are special clusters, because each node has up to 8 different GPUs, which is the maximum number that we can support today. And all those GPUs inside one node are interconnected with fast network layers, like, for example, with the NVIDIA GPUs, we use the NVLink connection. This improves the distributed training performance inside the same node. But of course, we have several nodes, so each node is connected to all other ones using another fast network layer, which can be, for example, InfiniBand or Slingshot. Just to provide some numbers, we are talking about 200 gigabits per second. And because we can have even 2, 3, 500 GPUs training at the same time on the same model. And also the storage layer is very important. It must be fast, so at least SSD drives. And because the datasets are accessed very frequently during the training process for all the processes running inside the GPUs. So the clusters we have now are converging to the HPC clusters because there is this convergence between AI and HPC, because the power which is required to train those models is starting to grow very quickly.
Good. With that exponential growth, and if we're talking about on-prem situations, Pierre-Nicolas, what's the best way to enable continuous training, continuous deployment with on-prem? If we're talking about offline constraints, how can that be once again be part of the solution and not the problem?
Yeah, sure. That's a great question, and like the answer will be different, I think, for every kind of companies or clients or people that you will talk to this, because you can have some. You are not necessarily offline, but you can be. You can have some, let's say, dual deployments, because at least in like image use cases. So usually we have different cameras on different machines that can be in different locations for different customers. So that can lead us to a lot of different sources of data that we must aggregate at some point, but also the privacy and the ownership of the data must be preserved on, for example, our plant or device, let's say, context. So for every deployment, like for example, if you want to take PICSELLIA to manage like the life cycle of the different models and data, like you have to wonder how will I monitor? How will I can I do this device per device, or can I do it on a plant base so I can aggregate the data on all my plant and see, as Ed says earlier, like is all the image transformation or the images still at the quality level that we think they are, or can we do we have to do it at the like organization level? So for example, you have one successful deployment, you deploy it across multiple plants. How do you make sure that your model is still relevant in all the plants that you have? And depending on what you want to do and how you want to achieve this, but also of the ownership of the deployments. For example, if each plant is responsible of the models that are deployed on their premises, maybe they can stay with like an on-premises full offline solution. But if, for example, you're a really large company like Airbus, or I don't know, you must do something that is company-wide. So at some point, you have to synchronize all your data and make sure that everything is up to date with the correct standards that can come from also different local solutions.
And imagining, rolling something like that out in a large-scale organization, whether it's Airbus or Coca-Cola, it doesn't matter. The resistance that can be met because one department does something in one way, it's done another way in another. Anticipating that, what we say in Spanish, you don't want to die from success. With that in mind, in terms of optimize, when we're talking about deployments, Ed, in your case, when deploying models at scales, what are the optimizations that you're working on? What are the fine tuning that's happening to make sure that things run as smoothly as possible?
Yeah, a great question. I think obviously like the main title for this panel is like optimizations of these data intensive deployments. But the interesting thing for us at SELDON is that we don't. Whilst we're a tooling provider, we don't provide tools that let people train models. So we do nothing in the training, the data space, any of that, right? It's what I like to say is we do the last mile of machine learning. It's like deployment and monitoring and things like that. But what that means, right, is that we, whilst there are techniques people can use to optimize the models for inference, like, quantization and pruning and stuff like that, we can't really like do that for our customers because they've already trained the model before they give it to us. So what we have to look at is how can we optimize things given the model that we have, how can we optimize the way that runs? And so what we found is we can do some clever things like, so we have an open source inference server called ML server. And we do in there, for example, we do things like adaptive batching. which will look at, like, for a certain window, if you get a bunch of requests come in, let's say every second, let's batch them together and send them to the model for inference as a batch, because that's way more efficient than running, a single prediction, let's say 100 times in a second, right? And maybe, 1 second is a threshold that's acceptable to be able to return the response to each of those 100 users. Another thing that we look at is how can we optimize the infrastructure underneath. So, if we've got a situation where you want to run 50 models, do you really need 50 instances for those? The answer is probably not for a lot of lightweight things. And so what we do is we try to load models onto appropriate servers alongside other ones. So a technique we call multi-model serving, which again, allows you to load multiple versions of models, multiple models of the same framework and runtime, that kind of thing, and have them share infrastructure underneath, particularly when you come to things like GPUs that can be pretty expensive. So yeah, that tends to be the kind of thing we focus on in that space.
That's great. I think 2023 has been a very strong year for talking about, optimizing hardware. Optimizing infrastructure. Once again, the stakeholder aspect. Everyone becomes a relevant part of the problem or part of the solution in an ideal situation, and it's something that definitely can't be overlooked. With regards to a couple of questions that we got in the chat, so Andrea, I'd like to direct this one to you, and then take it a little bit further because talking about training models. Someone asked about, from a hardware perspective, what about Raspberry Pi boards or NVIDIA using that for training models? Anything you'd like to comment on that?
Yeah, well, we don't have hardware like Raspberry because the models we have are very large. So typically the entry point for the GPU is the NVIDIA A100 with 40 gigabytes of memory. 40 gigabytes. And when we talk about big systems able to handle a lot of different models and also big models, the solution we propose is the NVIDIA 100 with 80 gigabytes on board. So you see, and
capacity. Yeah.
Also on the performance side, we have thousands of cores inside each GPU. We need some professional hardware, which is not only well supported, but also proven to work on different environments, heavily cooled, and in some cases with some hardware redundancy, because we don't want that the GPU breaks and we have to stop the entire node, for example.
All right, with that in mind, can you just walk us through the process, though, of where does the transition happen between going from end to end when we're talking starting from training and finishing with prediction? What are the steps that are involved in that process?
Well, yeah, we have those three different processes. One is the data management, the other is the training, and the final one is the prediction or inference. We have a lot of tools, both commercial and also in the open source ecosystem. On the data management side, we need to manage repositories because we need to track our data, to version the data so we can go back in time and see what we used to train a model. This is fundamental if we want to debug a model which is not working. And we also need some sort of tools to implement the pipelines because this is an end-to-end process. So it has many steps that we may want to implement and take different actions depending on the outcomes. So in these cases, for example, we use Pachyderm, which is open source and provides both of those two functionalities, repositories and pipelines. For the training side, we rely on Determined AI, which is another open source that we acquired. And using this, we can train models at scale. And on the inference side, we have also a lot of choice. Mainly, we have SELDON, we have KeyServe, and implementing the pipeline, we not only have the deployment aspect, but we also have the monitoring aspect because we want to monitor any drift on the data or on the model. And we also want to to validate the model maybe before going into production. And at the same time, also on the data management, we may want to implement processes like data augmentation or data cleaning before going into the training process.
Okay, very good. We got a couple of questions in the meantime from the audience, and so one I would like to refer, and we're getting close to the end, but I wanted to jump back to one that was directed towards you, Ed, and then we'll move forward. So in regards to the data at inference that Ed was talking about, would collecting other metadata from users at inference time be comparable to running transformations on the input data for that inference?
Yeah, that's a great question, and yeah, I kind of picked the example of kind of doing some image transformations and kind of enhancing the image, but yeah, that the point is that can be anything. We see a lot of use now of online feature stores, right, where maybe a user ID is the only thing that gets passed to the actual model or the inference system. But then, we retrieve all the important information and features about the user from a feature store. It could be things like third-party APIs that get called. If you're building a recommender system, but you want to put in the live weather from where that person, their location is, you might find that you can actually build a much better model doing that. But it means you need live data, right, when you're running inference. So all of these little transformations or data retrieval processes, or potentially even other machine learning models, right? Because sometimes we combine one model into another, etc. All of those can kind of be treated as units within this inference pipeline, right? And we have that concept of a pipeline that we use for inference. Okay.
We got another question from the audience. This one I'll direct towards Pierre-Nicolas. You can take a look here in the chat. We got a question up above a little bit from Alex Toe, asking, I configure the inference pipeline in 2 stages. First is on mobile devices to get the basic feature extraction and representation. Second, the extracted feature map is transmitted to the cloud for more heavy inference. Then the second part, the cloud side model size is and required GPU memory is 1 GB. A100 is 40 GB. My question is, in the case of thousands or more inference requests, how can we design the cloud architecture to give real-time inference?
So I believe that Ed answered the first question with the fact that we're not talking about only API endpoints for one model, but we prefer to have a real pipeline of inference that we have different bricks of different models that can act together. For example, we can extract a feature map, then we can perform, as Alex says, some more heavy inference in the future. And then the client that is calling this API endpoint can get the full answer of the request that went through this whole pipeline. So I think that it's important to remember, and we saw that with the growing maturity of the companies that we worked with, because at first they just wanted to have their classification results or object detection results. And we saw that while they were growing, they tend to go through different, more and more advanced pipelines, doing some other stuff with their prediction results. So that's the first thing. And as for the second question, I think that, and that's also something Ed answered before, but you would rather batch your request so you can really leverage the memory that you have on your GPU. And also, it's not a bad idea to have different versions of the same or different models on the same GPU. You don't need to have 100 of servers to have the same number of models that are actually served. So yeah, that would be a great way to leverage. And as an example, if you want to look at the open source side, you can go see what NVIDIA Tritons enables you to do, because they really help you leverage this kind of multi-models and multi-pipelines inference infrastructure.
Okay, fantastic. Someone also asked, and we can do this later on the chat, about sharing all the different, the open source projects that Andrea mentioned. So I'll actually bring it back to you, Andrea. If you can talk about those really quickly, but also 30-second summary, we're getting towards the end. What are the things that people need to think about moving forward? What is absolutely essential? What do you think just simply cannot be missed? So we'll start with you, Andrea. First, can you tell us about the open source projects you mentioned? Because we had a question about that. And then let us know in 30 seconds what you're looking forward to in the future, what you think should be on everyone's radar.
Yeah, this is a good question, because as you see, the AI now is a hot topic. There's a lot of movement, not only from the company side, but also from the research point of view, because the models are becoming smaller and smaller. We started with models like ChatGPT, which can be big in size, up to 1 terabyte. To smaller models, maybe even 10 times smaller, because they want to fit this into smaller devices to have it working not only on cards, but also on common hardware that we may use today, for example, mobile phones or any kind of small device, maybe also on other devices that we have, like the television or stereo. Maybe you see Alexa. Alexa is an example, very early about the AI, but this is the way we are going.
All right, great, perfect. Next up, Ed.
Yeah, I think I probably agree with that. You know, the large language model hype is very real, but for a very good reason. And I think that the open source models excite me a lot. I think, you know, they're getting better and better every day. And as they come down in size and they get optimized, it'd be really cool to see those running on like consumer grade hardware and eventually edge devices. Another thing that excites me is the combination of these like large language models and generative models with more like traditional ML workloads, you know, tabular workloads, general like, you know, image classification things. The combination of these in inference pipelines, I think, will allow for some really, really cool use cases.
Very, very good. Excellent. And last but not least, Pierre?
So that are some like great insight, but to give something a bit different. So we talked about data-centric like vision a bit earlier. And I believe that if you like the only thing that you have to do, at least if you want to be successful in like deploying, like transforming your models into real pipelines that go to production, is the ability to actually see and check the data at every step of this pipeline. So that's like, go back to my answer a bit before, but you have to be sure of what is the state of the data at each and every part and who owns this data to make sure that your project will be successful and that you will get some return on investment from a business perspective, obviously, at some point with AI in production.
Very good. Last thing we got to do, shout out to our amazing artists. I think we can get a round of applause for our wonderful panelists. So if you can click the applause button, that would be great. Very, very insightful conversation. Once again, there's so much more that we have to talk about. So very much looking forward to engaging with all of you in the future and hearing more about how things progress. So thank you all very much for your time today. Much appreciated.
You're welcome.
Cheers. Thanks. Take care.